Hello, everyone. My name is Christophe Corbier. Okay, and the subject of my presentation is our complex Finsler information geometry applied to manifolds of system. And I will do an introduction to the Q information geometry. Okay, outlines the classical first introduction, and second, what is the Q information geometry, and third, an experiment results, and I will finish to the conclusion and perspective. Okay, that's the beginning of this work is the system identification. What is the system identification? In fact, this is to estimate system model structure from measurements. And we carry out an estimation of parameter vector, we use either the classical estimator such that least square estimation or or the least sum of absolute deviation of LP. But sometimes outliers are in dataset, and the user can use a robust estimator such that L2, L1 Huber's M estimate or LP2, LP1. Okay, and the final step is the validation of this estimated system model. Okay, so this is the first step, and in fact there exist two kind of system. This is the minimum fast system, and the minimum fast system have all 0 pores inside the unit disk. Okay, but there exists the maximum fast system, and the maximum fast system, some zeros are outside the unit disk. And for example of maximum fast system and the acoustic system. The acoustic system it's the propagative system, and when you estimate a system model parameters, we have some zero outside the unit disk. Okay. And what is the space and what is the information geometry related to these systems? Okay. And for minimum fast system, Choi and Mullerup developed the Kähler spaces, and they introduced the Kähler information geometry, leading to one metric tensor as the second derivative of the Kähler potential. Okay, so this is the minimum fast system, and notice that Choi and Mullerup focused on only signal processing. Okay, in my work, I focused on maximum fast system, and with maximum fast system, where some zero are output the unit disk, the Kähler spaces becomes the R complex Finsler spaces. And I introduced the R Finsler information geometry, okay, and leading to 3 metric tensors, G1 and G2. There are 2 Hermitian metric tensors, a square, and G3. This is a known Hermitian metric tensors, non-square tensor. Okay, and in fact, I generalize that this point of view and name the Q information geometry. Okay, what is the Q information geometry? This is a generalization of information geometry related to manifolds of system which external input or internal input x equals 0 or not x equals 0. And the first part is to define the parametric model of system. Okay, and we define the joint power spectral density, and after the logarithm of joint power spectral density, JPSD, as the clefstrom. Okay, and after we define the psi function. The psi function is the first derivative or the logarithm of GPSD with respect to z mu. Z mu is the zeros and poles of the system model estimated. Okay, and after we define the manifold of system MNSX. N is the number of zero outside the unit disk. S is the system, and X, this is the endogenous or exogenous input of system. After we define the Finsler metric. The Finsler metric as the modulus of the complex Finsler function, FQNGX, and G for G equal 1, G equal 1 corresponds to minimum fast system. G equal to 3 correspond to maximum fast system. Okay. And the first step is to define the parametric model of system. And this is a general model, a linear model. And when x equal to 0 correspond to minimum phase in the Choi and Muller paper. And the transfer function is equal to R model on MA model or HARMA model. Okay, and for maximum phase system in my work, I generalize with a maximum phase and x different of 0 with exogenous input. Okay, and I focused on Harewig's model as linear or output model as pseudo-linear. Okay, now define the joint power spectral density. The joint power spectral density is given by this following expression as the square root of the spectral of the power spectral density of the process model and of the noise model. Okay, and after we can define the manifolds of system. The manifold of system is given by this expression where coordinates is phi or is equal to GPSD with integral condition. Okay, here define the psi function. The psi function, as presented, is the first derivative with the z mu, with the logarithm of the GPSD. And we can compute the psi function in this case as a sum of the psi function related to process model and the psi function related to noise model. Okay. And now, what is the Q information geometry? And the Q information geometry has 4 main parts. The first part is to define the R complex Finsler subspaces. The R Finsler subspaces is defined by this one. Such a space is a pair of manifold of system and the Finsler metric. QW is a Finsler metric. Finsler metric is defined by 3 conditions, 3 fundamental conditions, where the third condition is very, very important because this is the homogeneity condition. And lambda is either complex or real. Riza in the 60s introduced the complex Finsler theory, and with lambda as a complex. And Monteanu introduced lambda as a real. Okay, and we can see that the Finsler metric is a function of z and omega. Z is the zero and poles of estimated system model, and the omega as the derivative of z mu with respect to tau. Tau is equal to t in physics. Okay, but in my work, in our context, tau is equal to estimator parameter. Okay, And the second part of the Q information geometry is to define the Q metric structure. The Q metric structures is defined by an Hermitian metric structure and a non-Hermitian metric structure, because this comes from lambda is a real. If lambda is a real, leads to Hermitian and non-Hermitian. Hermitian tensors and non-Hermitian tensor. Okay, and the third part is to define the Q metric. The Q metric is the difference between two estimated system model, two adjacent estimated system model. Okay, this is the metric. When we have here the metric tensor, okay, and you have here the psi function, okay, and you compute this term, we obtain three tensors, G1, G3, and G1, G2, and G3. Okay, and the fourth part is to define the Q space. The Q space is the union of all R complex Finsler subspaces. Okay, such a space is a pair of manifolds of system and the Finsler metric. And the Finsler metric is the modulus of the complex Finsler function as defined by this. Okay, so this is a complex function where the real part is an Hermitian metric and the imaginary part is the non-Hermitian metric. And the modulus gives Finsler metric. Okay, and for minimum phase system, minimum phase system, G equal 1 and the alpha equal to 1. For maximum phase system, G equal 3 and alpha equal to plus plus minus. And this is the signature of the metric. Okay, experimentum. Okay, and as previously presented, maximum phase system comes from, for example, a propagative system. And in my thesis, I worked on this system. And this is an acoustic duct for active noise control. And the first step is the system identification, okay, leading to an estimated system model. Okay, and we use an IRIX model and output error models. And for the estimation function, we use an L2, L1 function. And this is the Huber M estimate, the classical M estimate. And you can see the slope threshold of M estimate, the parameter tau. This is the Finsler parameter in the omega. Okay, and when some zeros outside the unit disk is characterized by the z mu O. Z mu O is the number of zeros outside the unit disk. Okay, and this term, this is the estimated transfer function of systems. Okay, and here, and this is the Finsler coordinate omega between the difference of z mu with respect to the Finsler parameter tau, and this is G1, G2. This is the Hermitian metric tensors, and this is the non-Hermitian tensors. Okay, and the result, we put 50 values of the Finsler parametric tau, and we obtain 27 estimated models with 4 zeros outside the unity disk, and 33 estimated models with 3 zeros outside the unit disk. Okay, and the Finsler metric. Okay, and in this work, I introduce a new graph named Q graph. In fact, this is a Z-plan, just a Z-plan. Okay, why Z-plan? Because there is in a real part and imaginary part. Okay. And the first graph is the Q graph, and the Q graph is also named model's trajectory. In fact, each point is the imaginary point, is the imaginary function and the real function of the and this is the trajectory of each model with respect to tau. Tau is equal to Finsler parameter. Sorry. And this is the Q graph for 3 exogenous 0, 3 zeros outside the unit disk. And this is the Q graph for 4 0 outside the unit disk. And you can see that in the 3 0, there is a spreading of models trajectory. For the moment, I don't know why. We could investigate of this. And this, the second graph is the Finsler metric. This is the modulus of the complex function for 3 zeros and for 4 zeros. And in order to see the good fit of estimated system model, we represent the frequency, the magnitude, the frequency response of system. Okay, the model with respect to the system. Okay, and we can see that for 3 exogenous 0, the good fit in the Shannon interval, especially in low frequencies for control. Okay, in conclusions. In fact, a short conclusion. In fact, my work, we can distinguish 2 systems, a minimum phase system and maximum phase system. Okay, and the minimum phase system, we can represent each model in the Q graph as a model trajectory. And for minimum phase system, the trajectory is only on a real axis. And where some zeros are outside the unit disk when imaginary axis appears. Okay, the perspectives are very large because this is just the beginning of this point of view of the information geometry related to this maximum phase system. And the first part is to analyze the nonlinear and linear connection, and after geodesic and curvatures, and maybe an analysis of the metric such that the Randers metric or the Kropena metrics, and another system model structure as Armax. Okay, it's very large. Okay, this is the bibliography. Okay, thank you.
Thank you very much. Are there any questions, please? Yes.
So, can you go back in one of the first slides where you were comparing the minimal phase and the maximal phase in Q information geometry? One of the first ones. Okay. So, the two situations determine different geometric structures. So the two different settings.
Yeah.
They determine different type of manifold. So in terms of complex and real.
Is a complex manifold.
Both are complex.
Yeah. In fact, it's a complex manifold since the manifold is given for with respect to the Z mu. The Z mu are zeros and poles, and we know that 0 and pole can be imaginary complex, and there are some zeros and pole real, but if in fact, if the complexity is high in the system, in the estimated system model, a more complexity is larger, or more there are the mu as a complex. And this is the fact that in fact, Choi and Murope it's a very interesting paper, because this was the beginning of my work, and they focused only on a minimum phase system and the signal processing that is endogenous input, not exogenous input. But why not? And in fact, for maximum phase system, because sometimes when you estimate a system model, you could have models with zeros outside the Yoli disk, and this was my case in my thesis, but not the relation between my thesis and system and information geometry. But in fact, there is in fact the Kähler spaces is really focused on because the Kähler spaces leading to Kähler manifolds as a complex manifold, and the metric tensor is Hermitian.
Okay. Other questions? So if not, I have a small question myself. I wonder, when you introduced the Q information geometry, I believe it was slide 8. What exactly, when you introduce that homogeneity condition, what does it mean from the point of view of the system, physically?
It's the good question. In fact, for a system, I don't know, because it's just the beginning for my work. But in fact, the homogeneity or the homogeneity condition has been a high condition given by Finsler at the beginning of this of this theory, and I prefer to say I don't know, but for the moment I don't know.
Future work.
Yes, it's not easy for us to make a link between mathematical aspect and the physics aspect. So sorry.
Okay, thank you very much. Let's thank the speaker again.